So, this class I will discuss how we can generate a load settlement curve by using the theoretical approach. So, that first approach that we will discuss is proposed in 1966. So, that approach where we can discuss how we can propose the load transfer method. So, suppose if we have a pile, okay. So, this is a pile, single pile whose length is L, okay. And then when we apply a load on the pile, say Pu is the ultimate load, then we will have a tip resistance, that is Pp, and then we have friction resistance. Okay. So, that friction resistance is, say, this is the tau is the friction resistance. Now, what we are doing, that we are dividing this pile into number of segment. So, this is the first segment, say, okay, and where this first segment. So, there will be a Pu at the top, and this is the segment number 1, and again in all the segment there will be a shear resistance, and that is tau 1 for the first segment. And then we have a reaction at the bottom, that is, say, P2, okay. And then at the center, so this is the center of the element, say at the center there is a deformation del y1. So, del y1 is the deformation of the pile segment number 1, and the deformation is at the center. So, del y1 is the center deformation of the segment number 1. So, that segment is, say, L1. Okay. So, this is the segment 1. So, here 3 segments are taken. So, if you want, you can take more segment also. So, this is the segment 2. The similar forces will act here. So, here reaction is P2. So, that will act here P2. Then there will be tau. Now, this will be tau 2, this is second segment, the deflection at the center of the second segment will be del y 2, then there will be reaction, that will be P 3, and the thickness of the second segment is L 2. Now, there is a third segment. Okay, so, this is P 3. Then there will be tau 3, then there will be, okay. So, now this is acting on the tip, that means this is the bottommost segment. So, there will be a deformation in the bottom also. Okay. So, now here we are taking this is Pp, because here it is Pp. So, there is a deformation at the bottom, that deformation is del yp, that means del yp is the tip deformation. And similarly, here also there will be a deformation at the middle portion, and that is del y3. And then the thickness of this last segment is L3. Okay. So, now for the bottom there is a deformation of del yp, and the tip resistance is P p. Now, if we take that these piles are resting on springs, okay? These piles are resting on spring, and then this spring's constant is K S A. Okay? So, now we can write that P p, which is the tip resistance, that will be equal to, that means the, as I have discussed during the beams on elastic foundation part, that if at any point the stress Q is equal to K S into W. So, but that is the stress which is kilonewton per meter square. K s is the spring constant which is kilonewton per meter cube. So, into W is the deformation. So, here this is Q is equal to K s into W is del y p, okay. But here P p is the force. So, you have to apply the area of the pile or base area of the pile. So, finally, I can write this is A p into K s into del y p. So, where K s is the modulus of subgrade reaction. So, this is modulus of subgrade reaction. So, if you know the modulus of subgrade reaction of that particular soil at that site, then if I know the area and if I know the deformation or del y p, then I can calculate what is the tip resistance. Okay. So, now for the first trial what I will do, so this is the first step, we have to calculate the P p. And to calculate the P p, what we have to do, that for the first trial we assume a value of del y p, okay, assume del y p, we have to assume that. So, unless it is on the rock, that means the pile is resting on a rock, there will be a small value of del y p. Okay. So, that we have to assume, that means we have to assume a small value of del y p, and we know the A p, we know the K s. So, that means the A p is the area of the pile, pile base. So, that is a known, and then the K s is also known because this is the soil properties. So, these are known. So, these two values are known. So, that unknown is what? We do not know what is the value of del y p, because A p is the area which is known, area of the pile base, K s is the soil property which is known, but we do not know what is del y p. So, first we assume del y p is a very small value. We assume that we know K s, we know A p, so we will get the P p. So, P p is now known. Now, for the second or the next step, that we have to compute the P 3. What is P 3? P 3 is basically summation of P p plus tau 3, because tau 3 is the frictional resistance, that means the stress frictional or the friction tau 3, and that is acting on the periphery of this small element 3, and the area of the periphery of this small element 3 is pi d into L 3. So, again now what are the unknowns here, because we know P p from this step, initial step, we know L3 because L3 is the segment, because we know the L length of the pile, we have divided it number of segments. So, that L3 also known because we have divided it. Now, diameter of the pile is also known. So, that means here unknown is tau 3. So, how I will get the tau 3 value? So, this tau 3 we have to again assume. Now, for the first trial we assume that del y 3 is equal to del y p, because we have assumed del y p. Okay. Now, we are taking del y 3 is equal to del y p. Now, what is del y 3? Del y 3 is the deformation at the center of the element 3, and del y p is the tip deformation. So, now first trial we assume the del y 3. Now, we will take the help of this particular curve. Okay. So, this curve is given for different pile movement and the soil shear strength. So, this soil shear strength is nothing but the tau. Okay. Now, how this pile curve is generated? So, that means to use this approach, so you should have this type of curve, that means the slip of pile and the soil, that means a deformation of the pile corresponding to the shear stress or the stress that pile is getting for that particular movement. So, for example, a movement of 2 millimeter, the pile shear stress is 50. That means, for movement of 2 millimeter movement, there will be a shear resistance of 50 kPa. So, that is the idea. That means, for 4 millimeter movement of the pile, we will get a shear resistance of around 90 kPa or 80 kPa, 50, 60, 70, 80, 90 kPa. Okay. Or around 6 millimeter of movement, we will get a shear resistance of 100 kPa. So, this type of chart we should know and we should have. So, this chart, if you do not have any chart or curve, this type of curve, we can use this curve, but it is better that you should have your own curve. So, how this curve is generated? So, that means by field instrumentation. So, the pile deformation at different points are measured, and we are putting, and then the strain gauge are placed along the length of the pile, and based on that strain gauge, what is the stress on the pile for a certain deformation, and other values are calculated. So, that means strain gauges are attached, strains are calculated for the pile for different deformation. Then for that strain, the stresses which is acting on the pile or the pile surface for a certain deformation is calculated, and then this chart is produced. So, for this particular case, we will use this chart. Your case also you can use this chart, but if you can generate this type of curve, then that will be better for your own soil, but otherwise you can use this curve. So, I will use this curve to explain this particular problem. So, that means by field instrumentations, this movement versus shear stress curve or shear strength curve is generated. Shear strength means that tau, that the friction resistance that pile is getting for a particular movement. So, that means this case, first trial we have taken del y 3 is equal to del y p, and del y p we have assumed a small value. So, now that value we are taking as del y 3. Once we know the del y 3, so that del y 3 means the deformation, then corresponding tau value we will get from this curve. So, once we get the del y 3, that value, and then corresponding tau we will get from this curve. So, once I get that tau 3, then I will get the tau 3, that is from the curve. So, that I will put here in this equation. So, now P 3 is known. Okay. Now, once I will get the P 3, then what will be the value of del y 3? Now, we have to calculate del y 3. Del y 3 is what? Del y 3 is the deformation of the pile center portion. So, that will be equal to the deformation of the tip, that is del y p plus deformation of the pile itself. So, deformation of the tip is the deformation of the soil. Okay. So, this deformation of the pile material, how I will get that? So, we assume that the load is changing linearly along the depth. Okay, it's changing linearly along the depth. So, the average load which is acting at the center. So, average load acting at the center. So, P 3 is acting at the top of the element 3 and P p is acting bottom of the element 3 and they are changing linearly. So, the average load that will act at the center will be P 3 plus P p divided by 2. So, we know that E is equal to P by A into L by del L. So, del L is equal to P A E into L. So, that P is this average P into L will be equal to L 3 here and then that will be A E. A is the area of the pile at element 3 and E is the elastic modulus of the pile. Okay. So, E is the elastic modulus of the pile and A is the area of the pile. Or we can write this is A p E p also. Okay. So, that means area of the pile and elastic modulus of the pile. So, that means you can see this second portion, this portion will give me the deformation of the pile, and that means that is equal to, that means the total deformation at the center is the deformation of the tip or the soil plus deformation of the pile. So, deformation of the pile material is the second part and del y p is the deformation of the soil and that is del y p. So, that will give me the deformation at the center of the element 3. Okay. So, that is here. So, now in the first trial we have assumed the del y p and then we calculated P p. Then we assume del y 3 is equal to del y p and then determine the tau from the chart. Once I get the tau from the chart, then I will get the P 3. So, now P 3 is known, P p is known, L 3 is known, A p is known, E p is known. So, these A p, E p all are known, these are known values. So, we will get a new value of del y 3. Okay? Because initial trial we have done, now we have a new value of del y 3, because now we put those values here, then del y p we have assumed already. So, we will get a new value of del y 3. Okay. Now, that del y 3 will check whether the previously assumed del y 3 and this del y 3 are within the tolerance limit or not. They should be same or very close to each other. So, previous assumed del y 3 and now new del y 3, if they are within the tolerance limit, then we will stop. Otherwise, now in the next trial, using the new del y 3, we will again calculate tau 3 and then again I will put the tau 3 and then we will get the P 3, and then once we get the P 3, then again we will get the another del y 3, and then again we will check it and it will continue, okay, unless the previously assumed or calculated del y 3 is equal to or very close to del new calculated del y 3. Okay. So, once we get the del y 3 updated one after iteration, then we will get the final P 3. Okay. So, now P 3, P p are known and del y 3 is also known and del y p is assumed. So, remember that always this del y p it is assumed, still it is assumed, but others values are calculated based on this assumed del y p. Okay. So, once we get the del y 3 and the P 3, the next trial will be, then again we assume for the second segment, and then we assume del y 2 is equal to del y 3, because now we know the del y 3. For the second segment we assume del, for the first trial we assume del y 3, for the first trial we assume del y 3, again we will calculate the P 2 now. P 2 is P 3 is known plus again pi d tau 2 L 2. So, pi d is known, L 2 is known. Again once we assume del y 2 is equal to del y 3, again by using this chart we can use the tau 2 for deformation and then tau 2. That tau 2 we will put here, we calculate the P 2 and then we will calculate del y 2, which is equal to del y 3 plus P 2 plus P 3 by 2 now. For the second segment, this will be L 2 and A p E p, the same like the third segment. So, here also your for the second trial. So, this is the y 3 is the deformation for the center for the segment 3, and then we get the deformation of y 3 plus the deformation of that segment. So, that means the del y p that we are talking about, this is the deformation at the tip, and then we are calculating the deformation of the pile material, that will give you the deformation at the center of any segment. So, that means the deformation of the pile tip plus deformation of the segment 3 will give us the deformation at the center of the this third strip, and for the second strip deformation of the center of the third strip plus the deformation of the pile of the second strip. So, that way you have to add, because we have added the deformation of the tip, we have already considered. Now, every time we have to add the deformation of the pile segment. Okay. So, that means first one we have to add the deformation of the pile tip plus the deformation of the third segment of the pile segment or the pile material. In the second one, so this deformation you can see, this deformation is the summation of the deformation of the, this is del y 3, in that deformation also we can replace it this. Okay. So, now if I keep on adding, so that means we can have the deformation of the tip plus summation of the deformation of the pile material for each segment. Okay. So, now we have this deformation. Now, we have initial assume that del y 2 is equal to del y 3, then we calculate the tau 2, then we calculate the P 2, and now we put these values. P 3 you have already calculated in previous segment. Now, again you will get a new del y 2, and then again we compare the previous del y 2 and the new del y 2, and if it is within tolerance limit we will stop, otherwise this process will continue. Now, we will go for the next trial or the next segment, and that segment also okay. So, we have del 2. Now, for similar way we can have the that segment also, and that segment we can put that this is P u, because this is for the top segment, that is P u, that will be equal to P 2 plus pi d tau 1 del 1. Okay. And then again we will continue, we will consider that del y 1 is equal to del y 2 for the first trial, and then we will continue the same thing here also. Okay. So, and then based on that we will calculate the del y 1. So, this del y 1 will be equal to del y 2 plus P u plus P 2, P u plus P 2, yeah, P u plus P 2 divided by 2, then L 1, A p and E p. So, we will continue this thing. So, and then based on that we will finally calculate the P u and other values and the deflection also. So, finally, what would be the P u here? The P u I can replace the P p P 2 by P 3 plus pi d tau 2 L 2 plus pi d tau 1 L 1, and P 3 also I can replace by this equation. So, this is P p plus pi d tau 1 L 1 plus pi d tau 2 L 2 plus pi d tau 3 L 3. So, this equation will be P p plus, if the pile has a uniform diameter, or you can keep it is inside, this is L I, then pi d I or pi d into tau I. So, by the trial, if I know the L I, pi d also know, it is known. So, only we have to know the tau I. So, for every segment, if I know the tau I, then if I add them, then you will get the P u. So, we have to know the P p only, and then the P p will get by using these equations. So, if I assume this value of del y p, we know the case, we know the A p, so we have the P p. Now, that P p we will put here, and then we have to calculate the tau I for every segment by using this chart by trial and error method. So, once we get that values, we will get the ultimate load carrying capacity of the pile. And what would be the deflection of the pile? The deflection of the pile, the total deflection of the pile is equal to the summation of del y I. So, summation of all del y I will be the deflection of the pile. Okay. So, if I add the summation of each center point, deflection of each segment, that will give us the deflection of the pile. So, that means, by assuming one particular del P u, we will get one set of or one P u versus delta. So, this delta is nothing but the deflection of the pile top. Okay. So, this delta is the deflection of the pile top, or I should show you that this is the delta part. So, that means we will get Pu versus delta for one assume del yp. Still del yp is assumed because all these values are calculated based on the assumed del yp. If I change this del yp value, then this Pu delta all values will change. So, that means we have to assume now different del yp and we will get Pu versus delta value or different Pu versus delta or Pu and delta value. So, that means you will assume different del yp value, we will get one particular Pu and one particular delta. So, finally, we will plot this load versus settlement curve. So, this is my, or we can say that this is the load, this is the load and settlement. This settlement is delta, load is Pu. So, once we assume different del Pu, we get one Pu and delta. So, that we will plot here. Then we assume another del Pu and we get another settlement and the Pu, and then we will plot these points over this load versus settlement plot, and then we will get the load versus settlement curve for the pile. Okay. So, this way we can generate a load versus settlement plot theoretically, but remember that in this method we have to take the help of this particular graph. Okay. So, in the next class I will discuss another approach which is called elastic approach. So, I will discuss how by using elastic approach also we can generate theoretically the load settlement curve of pile up to failure also. Thank you.